Okay, so here's the surprise. So we're going to do the calculation for this shape, which I'm calling a torus, and we're going to pretend that there's a hole down the middle here. So we've got faces on the top like that. Okay, you see those faces? But we've got a hole in the middle. Okay, so how many vertices are there?
Well, those are just the zone balls.
Right, the zone balls. Sorry, just making sure I'm in the shot here. So the zone balls are the vertices. How many are there? How do we count them?
Well, there's 4, 8, 12, 16 on the top and then 16 on the bottom.
Okay, so I'll write that down. There's 16 vertices. I don't know if that's on camera or not, but that's okay.
Well,
16 vertices.
It's on the top and 16 on the bottom.
Oh, geez, sorry.
There's
Thank you.
32.
32. I wasn't paying attention. Okay, so what are the edges?
What's the blue struts?
The blue struts are the edges. How do we count those?
Well, we can count on the top. There's 4 sets of 3 going this way, and 4 sets of 3 going that way.
Okay, so how many is that
24
on the top?
on the top.
Okay, so the edges, we got 24 on the top.
Plus 24 on the bottom.
But then we have these connecting.
Okay, so we got the ones in the middle that are going up. How many of those are there?
There's 16.
How did you figure that out?
Well, there's 4 and then times the 4 this way.
Okay, so 24 plus 24 plus 16 is 48 plus 16, which is?
It would be 64.
64. Okay, so we got 32 vertices, 64 edges. Now we got to figure out how many faces we have, and that's tricky because we got a hole here.
Yep.
Oh,
So what do we have?
let's count them the top.
Then
and
we
the
have
bottom first.
We have 8 on
8
the
on the
top,
top,
and
okay.
8 on the bottom,
8 on the bottom.
and the inside there's 4.
Ah, those are the sneaky faces.
Yeah.
The
The
inside
sneaky
squares
inside.
here. Plus 4.
then we have the ones this way. So we have 3, then 6, then 9, then 12. So we have 12.
So 8 plus 8 plus 4 plus 12, which is 16 plus 16, which is
32.
32. So our calculation is 32 minus 64 plus 32, which is
0.
0.
0, not 2.
That's
What do you think?
seems to fall apart.
So the Euler characteristic of a torus is 2. Right, of 0.
Zero.
0, not 2, like we were seeing before with those planar graphs. So it looked like before everything we would get 2 for everything, but I just showed you a shape, if you imagine a hole through here, where we do the same calculation and we get 0. Pretty interesting.
Yeah.
Yeah.
Pretty interesting. Anyways, so I just didn't want you to leave you with the impression that everything had an Euler characteristic of 2. So just to wrap up real quick, what did you think of this project?
Well, I thought at first when we looked through the book, I thought everything would have the Euler characteristic of 2, but then we saw this and then there wasn't. There might be more things that aren't.
Yeah, there might be more things. So a little bit more investigating to do here.
Yeah.
What did you think of this project?
It was pretty fun, and I was looking and I saw that a Klein bottle has an Euler characteristic of 0.
Interesting.
Where are the faces on a Klein bottle?
Yes, that is actually a very good question. And a Klein bottle is a shape we can even kind of understand a little bit.
Yeah.
We have a 3D printed one.
Yeah, we have some 3D printed Klein bottles, but there's even other crazy shapes. There's like a shape called a projected plane, which is very hard to even like imagine.
Mobius strip.
In a Mobius strip we could, so there's lots of interesting things. So this project starts out in graph theory, which is a lot about counting and things like that, but it also sort of goes in a direction of understanding shapes, which, do you know what the subject of understanding shapes is called?
No.
Topology. So it's a pretty cool project. I like this. All right. High five on a torus. Great job, guys.